So you have a differential equation and it is proportional to A, so we can go directly, well, you can do, if you want, you can do separation of variables, but you can go directly from this to, actually, there it is, one more. Wiggle it a little bit there. There we go. You can go directly to this. Save you all those steps. Okay? Really nice when you can go directly there. Problematic when you forget what it is you can go directly to. So if you forget that you can go directly to that, well, you can use separation and integrate both sides separately and rearrange. But once we get this, this is really nice because C is your initial value. And we have an initial condition that A is equal to P when T is 0. So again, as a shortcut, because you know this is an initial condition is right there, you could go directly to this as well. Do you remember in grade 12 calculus when we used this formula? I called it the PERT formula because it spells the word PERT. That's exactly that same idea. That was used for continuous growth in questions in grade 12 pre-calculus. So if you wanted to, in this question, if you knew the shortcuts, you would only have to write the blue box, and then you could go directly to the answer. If you're afraid you'll forget those things, you can still do it, due process of separation of variables, and then solve for C by plugging in 0, and write your final answer down. Colony of bacteria is growing at a rate. Notice that this rate does not, it's not written in the form of a number times B. So separate our variables. Move our T over to the other side. Integral of dB equals integral of this. Integral of dB, that's just going to be B. How do we integrate e to an exponent? Well, e to the exponent stays the same, but there would have been a chain rule, so we have to divide by 0.5. And our initial condition tells us that there was 5, one time was 0. E to the 0, of course, is 1. Solving for C, you get -1. Now we have our equation for B. How many grams will be present in 10 hours? Notice you can't plug the 10 into this equation that was given to you originally because that gives you the rate of change. That tells you how many grams, not grams, it should still be bacteria based on what the question, maybe the bacteria weigh exactly 1 gram. Oh, 5 grams, okay. Okay, we've got our units there. I just read bacteria at the beginning. That's okay. How many grams of bacteria would be even more appropriate in the writing? So now we can plug 10 into here and just get our answer to 3 decimal places. Is this which? This is eights. They look like lowercase deltas. No, they're going to be eights. Okay, so the number of bacteria in a culture increases at a rate proportional to the number present. That tells us we can go directly to this, because if I use dB dt, we know this is the situation. We can go directly to this exponential form. Now, if the number of bacteria was 600 after 3 hours and 19,200 after 8 hours, when will it reach 120,000? So because of the proportionality, we can go directly to the exponential form. And based on the information that we're given, we know that after 3 hours, we have 600. That gives us one equation where we still wouldn't know the initial amount, which I have as y naught here. You could keep it as c. And you wouldn't know k. If you plug in your second value, you would get a second equation where you don't know your initial value and you don't know k. And if you have two equations with two unknowns, then you can use substitution or elimination to solve for this. In this case, because I got the y naught, the initial amount by itself, I can plug it in here. Now I only have k to solve for. So we use natural log of both sides to solve for k. I like to put dot, dot, dot to show that I'm going to store my number and use all of the decimal places. And this is an example where rounding early, because you're dealing with an exponential equation, it can be really catastrophic. I took a course in university that looked at the limitations of calculators, because in exponential equations, rounding is more catastrophic than in linear equations or quadratic equations. And in this course in university, we would have to do calculations with a calculator and say, did you know your calculator keeps, you see 8, but it might keep 16, and higher level ones might keep 32 decimal places. And for the most part, all of your calculations, that doesn't matter. But if you do enough calculations with rounding to 32 decimal places, you will eventually get answers that are wrong. And so we would do things on our calculator and say, you never rounded on your calculator, and you've done enough calculations that not a single number in the answer you can trust. And I would get questions like, here's the answer. Which is the first digit in this one you can no longer trust, knowing how your calculator works? Just kind of feels a little bit bad because you guys probably trust your calculator quite a bit. You're like, oh yeah, all these numbers are right. But you can actually do calculations and eventually get no numbers that are right on your calculator, even though you've never rounded. It's So now that we've solved for k, we could take either the 19,200 or the 600, and we could solve for the initial amount. So when you have a system of equations, you can make two equations with two unknowns. First did that in grade 10 pre-calculus. You can solve for both of those variables. And then once you have both of those variables, now you have the actual equation. And if we wanted to know when it would hit 120,000, you can plug that in, solve for t. Of course, notice our answer is a calculator style question. And so if the answer to this question is 10.646, which is perfectly fine, okay, and we used the calculator all the way through, ask yourself if you could use your graphing calculator to make this quicker. In other words, once you have this equation, you could put this into y1 and this into y2 and just see where those two graphs intersect. And you might be able to solve for t a little bit faster. And if you can solve for something a little bit faster on your exam, that's an advantage. Because there will be some questions on your exam that are going to stump you, that are going to take some time. And so the more places we can save time gives you more time to problem solve on some of those harder ones. Newton's law of cooling. Have you taken this before in any of your science classes? Have you ever had a cup of hot coffee or a cup of hot tea and you're studying, and then a little bit later you go to drink some and you're like, oh, it's got cold. Or even a bowl of soup. You leave it for a while, and there's like the perfect time to leave it where it's like, oh, this is the perfect temperature. But if you leave it too long, you're like, oh, it's too cold. Okay? This is all based on Newton's law of cooling, and it involves exponential equations. If you put something hot into a cooler temperature, it will cool down. If you put something cold in a warmer temperature, it will warm up.
Attention staff and students, due to a medical concern, we are going to go into a hold and secure. Please stay in your classroom or enter the nearest classroom that you can at this moment. Due to a medical emergency, we are going to go into a hold and secure. We will not be ringing the bell. Thank you.
All right. So we've got this differential equation for Newton's law of cooling. The rate of change is some constant times the original function minus t, and t is the ambient temperature. That's the temperature around in the room. And we want to solve this differential equation for u of t. So again, if you have an equation like this, can we get the u on one side? And it's multiplying right now, so we can divide. Separation of parts, integrate both sides, we get our natural log, kt plus c. And now we're going to just do some algebra to rearrange things. Okay, so a little bit of explanation of what's going on here. Yeah, I don't know if I like all of this stuff. You're not going to be asked to do a question like this, but our constant is going to be based on our initial value minus the temperature, the ambient temperature. I'll write this down. So at time is equal to 0, our u is equal to our initial value. And plugging those things in allows you to solve for C, and then I plug that C value into my equation. Yes.
Is it K multiplied by D capital T or D little t?
Well, because there is, oh yeah, there's a little t here. But then but then this t, it's not, no, this is bad notation, I'm sorry. Thank you for noticing. This, because t is a number, and little t, so this should be a little t here and a little t here. And then when you do it, it's k with a little t here for time. All the way through. It won't matter in this case. We're going to do one more question. Using actual numbers, because sometimes with actual numbers, we can come back to this and it makes a little bit more sense. So an object is heated to 90 degrees and allowed to cool in a room with a constant ambient temperature of 20 degrees. After 10 minutes, the temperature of the object is 60 degrees. What will the temperature be in 20 minutes? So what do we know? This is from our previous question, the formula that we got. Okay. And if we plug in what we know the initial temperature is 90, the ambient temperature is 20. And if we solve for this, we could solve for K. So get your exponential equation by itself, take the natural log of both sides. Now that we've solved for K, if you want to find it after 20 minutes, you could just plug it in.